Okay. So yeah, I guess we are live in both three platforms: YouTube, LinkedIn, and Facebook. So once
Okay,
again,
super.
we are so happy to have you with us in our community. We can't really wait to. Okay, Carlos, thank you. All right, once again, welcome to our community in our School of AI Algiers. Okay. So, Sir Sfian, so we are really, really happy to have you with us and to share all your knowledge regarding privacy, preserving machine learning. So feel free to share all what you really researches about the field, as well as I am really like interested in the field of AI and machine learning. So the stage is yours.
Okay, thank you so much for the warm introduction. And also, okay, first of all, can you see my screen? Is it perfect? So just give me a feedback that you can see my screen. All right. Okay, I would just want to write down my screen. Okay, thank you for saying that. Okay, amazing. So let me just start by thanking the organizers, thanking the School of AI Algiers for the warm invitation. I'm really glad to be here. It's been Oh yeah, somebody muted me anyway. Yeah, so I had to had like a lot of events around Algeria, and I'm happy to also give this online talk to the community of School of AI Algiers and to all those data enthusiasts and people that are interested in machine learning and deep learning in general. And that being said, I will talk about a field which is relatively new compared to other subfields and micro specializations in machine learning, which is privacy preserving machine learning. So I would say this is a type of field which has emerged recently. So it's not that as let's say like as known as let's say standard machine learning models or computer vision, but it has a lot of potential, a lot of interest, and a lot of importance. We'll go through the motivation through the slides altogether. But yes, so basically the main aim of today's presentation is to make you aware of the importance of a field of privacy preserving machine learning, or simply PPML. So I'll be calling it PPML for the sake of simplicity. But yes, so I will go through the multiple details of PPML. What should we care? What are the different research that have been already done in PPML? What are the ways to handle and to strengthen the privacy of your machine learning model? And also the type of adversaries where people try to extract some feature and some insights from your model about your users' data simply from you by applying some black box access, which I will go through all those details throughout the presentation. All right. That being said, let me talk briefly about myself. So my name is Sofiane. I'm Algerian. I'm from Constantine. I'm currently based in Germany. I'm a PhD student in the University of Tübingen as part of a doctoral program called IMPRSS, which stands for International Max Planck Research School for Intelligent Systems, which is a big doctoral program that gathers and takes into account a big collaboration of the University of Stuttgart, the University of Tübingen, also the Max Planck for Intelligent Systems, and also Cyber Valley being the largest AI consortium in Europe. And I'm supervised by Professor Dr. Nico Pfeiffer, and my research group works on medical informatics. Yes, this is basically my lab, and this is the IMPRSS Bootcamp. And my research project is called Certification and Foundations of Safe Machine Learning Systems in Healthcare, which is a research project funded by the Carl Zeiss Stiftung, which means in German, the Carl Zeiss Foundation, where multiple research labs are trying to explore different axes of safe machine learning systems applied in healthcare, like transparency, robustness, ethics. And for myself, I work on the privacy part. So my research theme and research topic is privacy preserving machine learning. All right. So before starting and diving into the content and also more details about PPML, I will just briefly remind the generic and general machine learning pipeline. I do know that, well, for this audience, most of the people already know how a machine learning model is being trained, but let's say I always assume that there is this person in the audience who just started in this beautiful field of machine learning. So it's better to at least give them a small insight of how a machine learning model is being trained. And basically, we all know that data is the backbone and the oil fueling a machine learning project. So data is everything. So in order to kickstart and basically train a model, you need some data. So after preparing the data, pre-processing it, cleaning it, etc., you will train your model, and then you will wrap it and then deploy it in the cloud or in a system or in a prototype or an application, web or mobile application or whatever. And the thing is, in privacy preserving machine learning, we will really focus in this part, basically the data part and the model part, because the adversary we will understand together what we actually mean by an adversary, but the adversary will try to query your model to either somehow make your model make false predictions, or also try to reconstruct the data of your model, or basically infer some information about your user's data, which will harm your user's privacy. Normally, when you train your model and when people trust you by their data, you should, out of respect and out of data regulation, nobody should ever know the data and the data formats of your users. But because of some adversaries, they will be able to query your model and then reconstruct your users' data. That's why PPML, I would say, we're really going to focus on this part of the machine learning pipeline. All right. But before really going through the technicalities, it's really important to go through the motivation, because motivation is what drives learning. If I motivate you and give you the reason why you should care about PPML, you will actually learn and care about PPML. So it's all about motivation and reasons. So I would say that during one of the American elections, there was this company called Cambridge Analytica that somehow, due to a lack of security from Facebook, they were able to access some profiles of people that wanted to vote, and they were actually introducing some fake news against one of the candidates, so that this person will vote for the other candidate somehow. And they were super personalized news and personalized fake news in their news feed, so that really this person will directly vote for the other side. And from that time, I would say the awareness, though there was already papers talking about privacy preserving machine learning, but I would say because of what's happened in this American election, the let's say the not only the awareness, but people started to really think, okay, now we were giving a lot of our data in those machine learning models, in those deep learning models, or in AI in general. So we should care about saving our data, and we should care about preserving our data, thus having this field of privacy preserving machine learning. And after that, there was the emergence, like the clear emergence of data regulations and data policies that allows you, or at least constrains AI developers and AI researchers when they are using some users' data to actually care about not revealing their or not hurting their privacy. So in Europe, we do have GDPR, General Data Protection Regulation, and in the US, more specifically in the states of California, they do have CCPA, which stands for California Consumer Privacy Act. So we already start to have this data regulation, which is really good because right now, for instance, when you enter a website, before those regulations, the websites were directly analyzing your data without you even having your consent. And they will give you no information how your data is being processed, which data are being used, etc. But now they will give you this dialog box asking you for your consent to what we call as the accept cookies. And not only that, you're also going to have some details about, okay, why we're going to use your data. And also they will tell you, okay, we're not going to use really specific data, but really metadata, like your location and also how you're going to scroll over our websites, etc. So at least there is more transparency. However, we do know that even if you put regulations, even if you put laws, not everybody is going to follow them. And there will be some bad actors that we're going to call them and name them as adversaries that will always try to bypass those laws and regulations, and they always going to try to steal, hurt your model, and try to infer information about your users. So that's why we're going to introduce those adversaries and the type of access they have through the terminology. So PPML terminology. Here, let's say, so you train your model, you get your data, you train your model. This is, for instance, I just wanted to symbolize this standard neural network. And let's say you get this final trained model M. And let's say now, okay, so usually when you train a model, you want to open source it. You don't want to keep it in-house, right? You want to other people to benefit from your model. So that's why you will open source it. And for instance, in the cloud, in Google Cloud Platform, Amazon Web Services, AWS, or Microsoft Azure, depending on the cloud you're using. And so you're going to basically host it and make it open source, and then create a service, what we call as a machine learning as a service, or MLS, machine learning as a service, so that people can come and try to query your model and get predictions. So let's say now you train your model to diagnose if a given patient is having a cancer or not, a cancer A or not. So you train your model, then you're going to put it in the cloud, and then let's say a really small hospital or a really small clinic in a village will just gonna query, and they will have a set of patient data, let's say X-ray image or MRI image, whatever, and then they will query your model and get a prediction and know if their patients are having cancer or not, simply because they know that your model is robust enough and it has been trained on millions of data. So this is the beautiful thing of open source. And unfortunately, even though open source is amazing, and we all, I mean, if I ask you now in the audience, oh, anybody, what do you think about open source? I know all of you are gonna say that open source has a lot of advantages. But despite the various sets of advantages of open source paradigm, and in addition of having this various sets of data regulations, there are still people that will try to query your model, not to benefit themselves, but to hurt you and try to learn more about your users and also try to poison your model prediction. So that's what we call as an adversary or a bad actor. But that's why we usually call this person as an adversary. And you can see from this, the symbol that, okay, he's not a good guy. All right. And the adversary will have two type of access, right? So if your model is just an API, so you put it in the cloud, and then you just the only interaction between the adversary and the model is that, okay, the adversary will just send an image, and then he will get directly the prediction through a softmax layer. So just a set of predictions here, where the sum will equal to 1, obviously. So here the adversary, why we call it black box, because the adversary has no idea of the architecture of your model. If you're using an autoencoder, a transformer, an LSTM, the number of layers, if you're using more tangent hyperbolic activation functions, or rectified linear, or if you're using in the end a sigmoid or softmax layer, so he won't know all those details. He will only query your model, send the data, and get the prediction. Send the data and get the prediction. While a white box access, on the other hand, well, here, as the name somehow explicitly shows, the adversary will have complete access and a complete knowledge of your model. The weights, also the loss function you have been using, also the number of layers, the exact type of architecture, and so on and so forth. But I would emphasize mainly on the weight. So the adversary will have a transparent view of your model, that this model will have that the model, he will have a clear access to your weights. That's what you have to keep in mind. Okay, let's now go about the adversaries and attacks. So let's start with the white box access, and then the let's say state-of-the-art example is an adversarial attack. Here, the idea is that you will try to add some noise, where you will maximize the loss for the correct class, and you're gonna make the model predict another class. And let's say the strength of an adversarial attack here is that we visually both agree that, okay, this is a duck and this is a duck, right? We visually see it, but the machine learning, or let's say how a model perceives an image, we know that, okay, when an image perceives when a model perceives an image, it will see it as a matrix of height and width, where the intersection will be a 3 color channels, an RGB system, let's say. And a pixel is a set of values ranging between 0 and 255. So even though we visually, as a human, as a high level view, we do not see it, like we don't see a difference, much of a difference. However, a model will be affected because of the small pixel change. You will have a different and really a differing prediction. And here you assume that you have a white box access. For black box access, I will mainly summarize the type of attacks being 2 of them. So the inversion attack and the membership inference attack. So the model inversion attack is quite easy to understand. Just think of a model inversion attack as a decoder. So the idea here is, okay, you're gonna, at least in this paper, what they did is you're gonna query your model, and every time you will get the softmax layer, the prediction layer. You query, you get the prediction layer. You query, you get the prediction layer, and so on and so forth. And then they won't let you simplify the prediction by truncating the prediction layer. So they will only keep high values, not small values. So let's say you will use a threshold of 0.1. So if the value is less or equal to 0.1, you just have to round it, or like just making it equal to 0. And then what you're going to end up having is you will end up having a pairing data set, where you have the inference layer and the original input. And then you will just go like backwards. You will basically go from the prediction layer after the truncation towards the original data. And you do that using a decoder layer. And here they actually mentioned how, because of that, especially when they try different type of data, where, okay, they assume that the training data and the testing data are in the same distribution, similar distribution, or differing distribution. And they, especially when it is the similar or really close distribution, the model inversion attack is so accurate. And the idea here is, it's not about really reconstructing your data as perfect as possible. But if you still know the, if at least for a human, if you know the color of the skin, the gender, the ethnicity, etc., that's already some misinformation. Like if I was part of a data set, and they are they had like my face to train their model. I don't want somebody else to know that, okay, I'm wearing glasses and I'm white. So even if I'm not being recognized as Sofiane exactly, but I don't want to others, like an adversary, to know some meta information about me. So this will hurt the privacy, because now your users, and adversary will know some meta information about your users. Just to give you like here, okay, like here you can at least know that this person, reconstructed person, is a female. Just to give you an example. So this is a misinformation that normally nobody should know. On the other hand, we have a membership inference attack. And here, think of so I told you inversion model attack is basically a decoder. And here, just think of it as a binary classification. You want to know if a sample I was part of your training data set or not. And this is the trivial idea of here is, if your model is overfitted, so your model is not generalizable enough, so you will notice that that okay, when you will get the prediction of a sample that was part of your training data set, the prediction will really converge to 98%, 99%. While if you will get a new sample coming from the test set, then there you will have the prediction will be like 80, 85%. And this is bad, because still the fact that even me, if I'm taking part as a person, I'm giving away some data about myself to take part in a research project. I don't want an adversary to know that I took part in this project. So this is something private. So even the membership inference attack, even if it's like, okay, simplistic by nature, I don't want to be identified as a person who took part in that research project. Like I don't want people to know that, okay, my data was part of that research project. This is private. We agreed, when, at least in Europe, when somebody like a patient agrees to give away his data for the sake of your research project, so that you can work on fine tuning a model, you do sign something with him according to GDPR, that nobody will ever know that this person took part in a research project due to privacy issues. So by membership inference, we do, like, an adversary can hurt this clause, like this data regulation clause. Okay, now we went through so what we did so far is we went through the motivation, we went through the terminology, we went through the attacks. So we went through both white box and black box attacks. So let's go through the differences right now. Okay, so the first and at least trivial and easy solution, and actually a lot of people are still using this solution, is what we call as differential privacy, or Epsilon differential privacy. Here the idea is also easy to understand and to grasp. You just have to add some noise, a Gaussian noise or Laplacian noise, depending on your setting. And epsilon is basically the parameter in epsilon differential privacy that controls the amount of noise that will be added to your input data. And the idea is, okay, here you always have a trade-off between performance and privacy. So the smaller the epsilon, the higher the added noise. So the more privacy your model will be, or the more private your model will be. However, you are going to hurt the performance. While if your epsilon is big enough, so the bigger the epsilon, the less noise will be added, because it's like 1 over epsilon. So the less noise will be added, and thus the less private your model is. But on the other hand, the more performance your model is. So that's why somehow DP is not really attractive to some domains. So if you take healthcare, for instance, and you try to convince a doctor that, okay, your model will reduce and decrease by 1%, well, you know that by 1% you were going to risk some people's life, and that's why, as a doctor and out of scientific honesty, not everybody will accept this sacrifice, etc. So that's the thing about differential privacy. It's easy to implement, but it's hard to convince, because you're always going to sacrifice performance for the sake of privacy. Another type of like, let's say, more cryptographic way of applying PPML, or like for as a defense mechanism, is homomorphic encryption, or HE. Here, the good thing is those are cryptographic, assured, and accepted ways to somehow secure the computation. And however, so here they are, especially for operations like multiplication and subtraction and also addition, those are secure. However, the main problem is when it comes to activation functions, that, let's say, tangent hyperbolic or sigmoid or softmax. So here you have some like if you take softmax is 1 over 1 plus exponential minus x. So exponential, we don't have a secure way to apply homomorphic encryption. So there are some papers like this who suggested that, okay, you're going to apply some Taylor approximation, where you're going to, okay, turn your exponential into a set of addition or summation of some polynomials. However, here again, you're going to trade off some performance and privacy. So if the approximation is too generic, so you only take some polynomials, here, well, the computation will be fast, but you're going to still not going to you're going to lose performance. And while if the polynomials are big enough, the main problem is the homomorphic encryption will take a lot of time. So it's really time consuming. So again, it's not really attractive when you have a lot of activation functions and when you have a lot of nonlinear activation functions, because, okay, it does work on addition, multiplication, and subtraction, but not really on nonlinear operations. And here I summarize the pros and cons. So differential privacy, it's fast, and the con and the disadvantage of differential privacy is that it reduces the performance because of the noise perturbation. While homomorphic encryption, while it's a strong secure cryptographic method, but it's super slow to implement. And on the other hand, well, if you have, especially a neural network, will have some nonlinear activation functions, in that case, well, unfortunately, you will also lose some information because of this approximation, and thus you will lose some performance. Unless you would like to approximate towards multiple polynomials, but in that case, well, the main issue is you're going to, again, have a really slow computation. And imagine, okay, don't think about your school or like a university project, but think about, okay, implementing a really big transformer model. There, you're going to really feel this computational time. Okay, so also we do have some deep learning methods for the purpose of privacy preserving machine learning. So the main idea here is you will use some adversarial learning, where here you will fix a utility attribute and you will fix a private attribute. So utility attribute is your task, is your task goal. Like in this case, in this Amnis data set, the task is to recognize the digits, the number of your image of your digits between 0 and 9. While here they decide that the private attribute will be to hide the information of the number being odd or even. So here what they did is they want to create a decoder that will just create a, let's say, a privately kept or like a more robust and private, let's say they won't let you recreate an image that will hold and discard some private information here. So in the private information here, they want to discard that this number is odd or even. So how they do that is, okay, they just link to this reconstructed image two classifiers, one called the utility classifier and the other called private classifier. And as you can see in the formula, they want to minimize the loss of the utility classifier, because we would like to make our model or the image hold information about the digits, but at the same time discard information of the private attributes if the image is odd or even, by maximizing the loss towards the classifier for the private attribute. So here you're just going to minimize something, minimize the utility and maximize the privacy attributes. At least you're going to keep both of them, right? So you're going to make sure your model is performant, and in the same time you're going to really keep some privacy information. So it's better, it's more guided than just randomly add some Gaussian or Laplacian noise, and then you're just going to hurt the performance in general. A more practical example of this is, okay, you have this, so here they have some image where you would like to keep, so you have two attributes, a private attribute and utility attribute, where one is an army base and the other is like an airport terminal. And you see that, okay, now they do the same thing. So they fix, so they want to keep good information about, okay, this is an airport, while they would like to discard information about this being an army base, and so on and so forth. So that's a more practical way of applying this adversarial learning. However, if I just come back to those two slides, the main problem is here you have to explicitly identify one utility and one private attribute. And let's be honest, it's somehow hard to identify what is private. Is it the color of your hair? Is it the fact that you're wearing glasses or not? Is it like the color of your skin? The kind of shirts you were wearing that day, and so on and so forth. So you do have, being able to list and enumerate all the private attributes is not really easy, because this is personal. Something that is not really private for me might be private for you. So this is subjective, and that's why here that's the main, I would say, criticism towards this project, towards those architectures, is that you have to identify one excite and explicitly say that, okay, this is a private attribute. And on the other hand, here what they did is, okay, this time they just want to not really identify any private attribute, but just have maximize the perception loss and the mean squared error loss between the construction image. So that's why they would like to maximize the reconstruction loss, and at the same time make sure that the latent space is holds enough information for a specific utility attribute. So here again, you make sure that your latent space will include information about your utility attribute, and at the same time you would like to maximize the reconstruction loss. But here again, even the authors mentioned that, okay, the main problem is here, well, you still can infer some information about this person. So you don't know exactly who she is, but you know that, okay, she has a white skin, probably blonde hair, somehow, okay, white blonde hair, and also she's a female. So again, we still are able to identify this person. I mean, some meta information about this person. And there was this really interesting paper that appeared in ICML, who actually, I guess, they won the best paper award. So what they noticed is that, okay, if you have you basically, there's something called dataset condensation. And so to briefly describe what dataset condensation is, so you just want to create, so let's say you have a big chunk of data, million data points. This is your data, original data, but still you want to encompass it to a synthetic data set that is way smaller, and you would like to transfer it to other people that have less computational power. And in order to, what they do is here, they start, so this is the original data, the large original training data. This is the small synthetic data set, which is randomly initialized. And the thing is, they want to, through the classification, which is done in parallel, and through the pipe propagation from the loss, they would like to update the small synthetic data to be as close as the large training data, so that the weights here, they are like as close as possible. And the assumption from the dataset condensation is that this small synthetic data will hold as much important information as the large training data. So basically, you can now train your model on those 10,000 samples, which will give you as a performance model as if you train on this 1 million data points samples. Okay. And they noticed that, okay, if when you train your model on synthetic data that was generated from the dataset condensation, you also somehow you strengthen your model privacy towards membership inference attacks. So this is also, they prove that when you use dataset condensation, this will actually help privacy. So sometimes there are papers that show you ways to make your model more secure, like the ways that you, by training your model, you're going to make it less prone to some attacks, either adversarial, model inversion attack, or in this case, membership inference attack. Sorry. Yeah, and for our case, so what I'm exploring with my lab mates and my colleagues is, okay, we would like to also use encoding. So instead of, okay, now you like, okay, you, instead of reconstructing the image, because even in this reconstruction we can still infer some meta information, like the example of this woman. So what we want to do is, okay, what if now we're just going to talk through representation space. So I would like to create, let's say, what we want to do in our project is, okay, we want to create a a type of representation that contains most of the information, but in the end we're going to just send this representation in embedding space rather than the encrypted image. Because even this encrypted image, where you take off some private attributes, you still can infer other meta information. While if you only send a vector space, well, it will make really, even if your model is able to reconstruct it, he will only be able to reconstruct this vector space. But the main challenge is here, well, by sending only a latent space and a vector space, you will have less features, less and by less features, it means less information. That's why working is, like, we want to ensure that this representation is affirmative. It gives interdependency of features. It has some similar geometric distance, and also discriminative when it comes to your task, I mean your original task. So discriminative in the sense that, okay, the data points that are with the amnis 0 are way further than the data points that are for amnis 1, 2, 3 until 9, etc. Yeah, so basically the conclusion here is, since AI and machine learning and deep learning are all data centric. So by data centric, it means that you cannot do machine learning, artificial intelligence in general, and by extension, without data. So data is the backbone of your any AI project or any intelligence system project. And that is why when we are dealing with data, there will be some people that will try to bypass some regulations and will try to query your model until they will be able to get some information about your users' data, or they will try to poison your model in prediction by applying like adversarial attacks. Another thing is, we have to teach data ethics and good scientific practice in schools and universities, so that people, when they learn, and they will in the future be the future engineers of AI and the future researchers of AI, they will always keep the good seed of, okay, we're doing this for by the humans and for the humans. We're doing machine learning for the good of humankind. So that's why we should raise this positive awareness among people starting from middle school, high school, and of course university. And also we do, this is a main tip as well that you have to spread. We have to be pretty careful on overusing social media and exposing too much of our data, because by this overexposure, well, we're going more about our identity. So sometimes only by clicks, if you click too much on astronomy content, I do understand that, okay, you are an astronomy lover. If you click on this person too much, we will understand, okay, you like this profile and this type of content. And then you will just feed a recommendation system. So again, be careful. I know social media is a thing and nobody can bypass social media nowadays, but still, it's good to at least avoid overusing it and also giving away your data for free. That was it. So I would like to conclude that about myself also. So I did launch a YouTube channel which allows Algerian students to learn about data science and machine learning theory and practice, بالدرجة الجزائرية, so with the Algerian accent and the Algerian dialect. So yeah, if in case you're interested, I'm really covering like somehow 45 videos going from data platforms to like most of the machining models, like decision trees, SVMs, PCA, K-means, and I always cover theory plus practice. I do both because I'm a person really practical by nature. Yes, so in case you would like to really explore it, I will be happy if you can subscribe and also try to share it with all your network. And that being said, I'll be really happy to take any question.
Wow, really amazing presentation presented by you, Sufyan. We really like discovered like many things regarding our privacy of data and how it can really, while we are training our model, and regarding like the translation of our data into another API, it's not really that, as we all thought about it, that is really private, and it can change, our perception of how our basically how our models are trained on another API, if it's related on another API on the cloud, as you mentioned, or any or wherever it is basically hosted. So with this, we really, guys, conclude our AI summit talks, and we are really happy to have you with us once again, Sufyan. Really informative information. It certainly helped me, and as well as I'm sure, pretty sure of our my friends. And so when we are going to train our model in some sort of a cloud, we are not going to make it, hard for attackers to make it that simple. So we
Yeah,
are going
yeah.
to use, yeah. So
Good to
thank you
hear
really
that.
so
Yeah.
much. And for tomorrow, we are going to have in our research papers on presence. So we will be waiting for you guys and at Easy Algiers. So with this, I conclude with you, Sufyan, and thank you for our all viewers and that were watching our live on Facebook, LinkedIn, and YouTube. Thank you guys a lot, and I wish you a great night. Thank you. Thank you a lot.
Ciao, guys. Bye bye.
Bye bye.